Okay, so good morning, everyone. Today we are going to start a new topic from probability and statistics course. The topic is continuous random variable, and uh, it comes under the section 8.1. Okay, so today we will begin with this topic of continuous random variable. Okay, so in our earlier classes we discussed about what a random variable is. Okay, so this much you already know what is the definition of a random variable. Okay, and you also studied some examples of discrete random variable. Okay, so there is two type of random variable. Okay, so the category is, the first one is discrete random variable. Okay, and the second one is continuous random variables. So in this chapter we will study about continuous random variables. Okay, so what a continuous random variable is. Okay, so when our random variable takes values, for example, let me give you an informal definition that, uh, okay, so let me type it here, so it will be more better. So when the random variable, when the random variable takes, okay, takes values, continuous values, takes uh, continuous values. Okay. For example, all the values in an interval, okay, in an interval, closed interval closed interval A to B, okay. So this is one example where our continuous random variable is taking the value, all the values in an interval A to B, okay. So the continuous random variables takes values in intervals, okay. So this is the most important thing, that when the random variable takes the values in interval, okay, it is not required that if it is a closed interval, it can be interval of kind a b also, okay, or this semi open semi close sort of intervals can also be there, okay. And it is not also mandatory that this continuous random variable will take values in a single interval. It can take in union of interval also. So this continuous random variable, it can take the value A to B, A B interval, union CT. Okay. So X can belong to union of two intervals or more than two intervals. Okay. But it should be then union of finite number of intervals. Okay. So this is the nature of our continuous random variable, that it takes continuous value. Unlike the case of discrete random variable where the values were infinite, but you could actually count them. Okay, here you cannot count. For example, the number of values that this random variable taking. For example, if it is taking the values from A to B, then you cannot count the number of elements present inside this interval. Okay, so this was how a continuous random variable is. And let me give you an example, an experiment, so that you can understand how this type of random variable can emerge inside a mathematical model. So, for example, consider that this is a lake, okay? So, I'm drawing the surface of the lake, and this is the bottom part, lake or sea, whatever you want to consider, okay? Okay, and let me fill this blue color here. Okay, so it is now intuitive with this color that this is a lake, okay? So, at any particular point, for example, if this point I'm considering it as A, so I can measure this vertical distance, and this vertical distance will represent the depth, okay, depth at point A, okay. So now it is very much clear for us that this value of the depth, actually it will take continuous values, okay, because at this point will move in either in this direction or in this direction. The depth will vary, okay. Okay, so depth here like this. In different points, we will be having a different depths, okay. So for example, if the lake is like this, so at this particular point here, this point here, the depth will be 0. Okay, and it will increase in this direction. Okay, so depth is increasing in this particular direction, and again after certain point, for example from this point, it will again start decreasing. Okay, so if I denote some x, for example, if I pick this capital letter X, and X denotes the depth of the lake. Okay, so then X will denote a random variable. Okay, so X will denote the random variable, and X will take the value from 0 to some value capital M, where capital M is the highest depth of the lake. Okay, so capital M will be the highest depth. It will be around somewhere here. Okay, so this is the point. Let me show you in the green. This point here. Most probably this will denote the maximum depth of this lake. Okay, so this was the situation, this practical situation where I have given you an example, where this situation of this random variable, this continuous random variable may occur. Okay, so now in our syllabus we have very special type of random variable, continuous random variable, that is known as normal random variable. Okay, normal random variable. Okay, normal random variable, normal random. So normal random variable, just as in case of discrete random variable, we studied random variables like Bernoulli's random variable. Similarly, in case of continuous random variable, we will study the random variable that is called as normal random variable. And okay, so when we come to normal random variable, there is one important point that you should understand, that earlier, in case of a discrete random variable, we were able to actually draw the histograms, and okay, so it was known as, that curve was known as probability mass function. Okay, in the case of discrete random variable, we have this probability mass function. And now, in this random variable case, we will be having a graph known as probability density function. Okay, and it will actually represent it will be useful to calculate the probability. Okay, so let me show you how it works. For example, if I pick the same scenario of this lake, then what I can do is actually I can draw a graph. Okay, so here the 0 and the maximum depth will be like this. Okay, and I am drawing a curve. Okay, so let me draw a curve. So I just randomly I am drawing a curve. Okay, any curve. Okay, and what I am saying, that if you want to actually calculate the probability, if you want to actually calculate the probability of the depth. Okay, so if A represent the depth of from point A to B, then there is a function, this function f of x. Okay, f of x. If I want to calculate the probability, that what is the probability that particular depth is from certain point A to B, then I'm saying that in order to calculate that thing, we need to just find this area. Okay, area under the from limit A to B. Okay, under this. Okay, so it is nothing but area of curve under f of x from A to B. Okay, from limit A to B. Okay, when this is the case, when we are able to find such f of x, then this f of x is known as the probability probability density probability density function. Short form is PDF. Okay, so in this lake scenario, so this, if for example, if you want to find out what is the probability that certain the random variable is taking the value from one depth from A to B, then simply we need to just find the area under this curve. Okay, and I'm not claiming that this is the probability density function for our example of lake case, but I just drawn a rough example to show you how it actually works. If you how it differs from the case of a discrete random variable case. Okay. So here, one more important thing that you need to remember is the probability of any particular random variable occurrence is nothing but zero. Okay. So in earlier case, in discrete variable case, if you want to find probability of x equal to c, okay, so either it can be zero or it can be some positive number. Okay, in earlier case, in discrete random variable case. But in continuous random variable case, you need to remember that particular point is nothing but zero. It will be always zero. Okay, always. Okay, because for example, if we want to calculate that what is the probability that the depth at certain point is say certain value. Okay, so you can see that it is it because the depth is taking infinite number of values, so the probability of any particular depth or any particular chance in the probability terminology, it will be zero. Okay, and there is one more intuitive actually example to consider. For example, if this is a circular board on which some shooter is actually shooting for maybe practicing for Olympic. Okay, and if you want to calculate that what is the probability that the next shot is at this particular point. Okay, so I had drawn this red point there. Okay, red point there. So you can tell that intuitively the probability should be zero. Okay, because uh, is the probability is very much is negligible that any shooter will just shoot immediately at this given point. Okay, if for example, if we are saying that what is the probability that the shooter will actually shoot in this particular range. Okay, this blue dot. Okay, because now the area is very much large as compared to this single point, this red point here. So now we can actually assign some probability. Okay, there will be a positive probability here because at least we have some area. Okay, but this single point, okay, this single point will carry a very negligible probability that we assign at zero. Okay, and the scenario here of shooting, this will also be treated under the continuous random variable case. Okay, so that's why the probability of occurrence of any one particular point will be zero in the case of your continuous random variable case. Okay, so now for in the continuous random variable, the random variable that we will be studying in this chapter will be a normal random variable. Okay, so here they have given that a distribution function will represent a normal curve. Okay, so this curve, okay, this density function curve, in the case of normal curve we will get a symmetric curve like this. Okay, a bell shaped, okay, also known as bell shaped curve. Okay, bell shaped curve, it is symmetric about this line. Okay, it is symmetric in both the direction, and this random variable will be normal random variable. Then we have certain points. Okay, certain point that we will discuss and see that if a probability distribution is represented by a normal curve, then mean is equal to median is equal to mode. Why? Because see, the graph is symmetric. It is like this. It is symmetric in the nature. So mean is nothing but here. Okay, mean if denoted by mu. So the mean, median, and mode. Okay, so all these quantities will be same because the graph is symmetric. Okay, we will see this even further when we'll do perform certain calculation. But right now, just take a little glimpse of the abstract nature of the normal curve. Okay, the peak of the curve is at the mean. Okay, so the peak will be at the mean at this point, the mean, and this is where we find the first line of symmetry. Okay, so this point, this line will be known as line of symmetry. Okay, so this bell-shaped curve will be actually symmetric about this particular line. Okay, so we have covered these 2 points. Then the third point is that probability density decreases as we move away from the mean on both sides. Okay, so you can see that if we are moving in this particular direction also and in this particular direction also, the probability is decreasing because see, the probability is nothing but the area under the curve. So if you pick 2 points here, okay, the area will be smaller as compared to if you pick 2 points, two adjacent points of same width here, okay, because we will get a longer strip, okay. So the area of this strip here, A and B, area of A is greater than B. So the probability here will be more as compared to the probability at the point B, okay. Similarly, an increase in the standard deviation sigma means that the value become more spread out from the mean, okay. So for example, if we want to draw a curve with more standard deviation, okay. So that I have already, I think that I have pasted here somewhere. Okay, so let me draw a curve. So I will show you a curve, two curves with that have same mean, but the difference is difference in their standard deviation. Okay, so for example, if I draw a curve like this, okay, and if the line of symmetry is here, set here, okay, so it is mean mu, and if I draw another graph like this, okay, another graph like this. So now you can see that although both the graphs are normal, okay, so forget about this thing, it is actually a symmetric curve. But for the blue curve, we have the standard deviation sigma is less. If I denote sigma 1 for blue and for pink, if I denote sigma 2. So from the graph, it is clear that although the mean for both the curves is same, but since sigma 1 is less than sigma 2, so the standard deviation for this curve blue is less as compared to that of pink, because see the data is deviated till this distance, but for the blue curve it is only till this distance, because this curve will actually die out here. Okay, so for this mm, sigma 1, it is sigma 1 and this value sigma 2. Okay, so the from graph it is clear that sigma 2 is greater than sigma 1. Okay, so although both the curves are normal curves, both are normal curves, okay, both have same mean mu, but their standard deviation is different. Okay, so I think that we have pretty much covered all the theory and concept required for understanding of this normal random variable. So now we will jump on to one question that is present in your exercise. It is question number 5 from your exercise 8A. Okay. Okay. So let me. Okay. So I will show you the details in short. Okay. So the data is about some babies, newborn babies. It is about 444 newborn babies from USA, and it has mean mu is equal to 3.4, and the standard deviation is given as 200 G. Let it be. Okay, so it is about weight of these babies. That's why it is in kg, and then the standard deviation is in grams. And similarly, about 888 newborn babies in United Kingdom. Their mean is 3.3 kg. Standard deviation sigma square they have given 36100 grams square. So with the help of calculator, we can calculate the standard deviation. It will come to be 190 gram. Okay. So now, okay. So we can analyze this situation on a normal curve, and we will see how this data actually can be transferred in a normal curve. Okay, and then we can actually draw many conclusions just by looking at the normal curve. Okay, so for this USA, I am using this red, and for this UK, I will use this. Okay. So first of all, this data is 3.4 kg. So let me, if I'm denoting 3.4 here, so then 3.3 will be obviously left to this 3.3. Okay. And for 3.4, this mean we have standard deviation to be 200, but here the standard deviation is less. Okay. So if I am drawing the normal curve for USA to be like, see, you have to just draw approximate normal curve. Okay. It's not that. And before that, let me draw this line of symmetry. Okay. So If I draw the normal curve for USA in red to be like this, then for this UK, see, for UK, this standard deviation is less as compared to that of USA. Okay, so its graph should be uh, more closer to the line of symmetry, as it should not be much farther away. Okay, so let me draw the line of symmetry here. Okay, so this graph should be like this. Okay, it should be more narrower as compared to that of the other graph that is drawn in the line red. Okay, so they have different mean, they have different standard deviation. That's why in this case they are separated graphs. Otherwise, if they have the same mean and different standard deviation, then their line of symmetry will be same. Okay, so once you draw, now we have drawn the two graphs. They are just rough graphs, and you can draw many conclusions. Okay, just by looking at the picture. Hmm. Okay, so I think that you understood how I solved this question, and you also understood all the concepts about your what is a continuous random variable and what is then a normal random variable, and how we draw the probability density function for them, and what with the help of probability density function we can actually calculate the required probability. Okay, and I also demonstrated this concept with the help of one exercise given in your textbook, how we draw this curve. So this was all from my side for this session. Thank you, and I hope to see you soon. Thank you very much.